A basic query-to-vector database to LLM pipeline is an excellent prototype, but when exposed to massive enterprise-scale data, it shatters. The top K nearest neighbor approach falls apart the moment a user asks a complex, multi-step question. The engineering bottlenecks are mathematically persistent. Users submit vague queries. Semantic search returns noisy, irrelevant chunks. And when you feed a large language model low-quality context, it hallucinates. To fix this, you have to dismantle the pipeline. Production Retrieval-Augmented Generation is a modular engineering discipline. You must break the system down into 3 distinct operational stages: pre-retrieval data preparation, the retrieval search mechanics, and post-retrieval context sculpting. We are going to execute a chronological, encyclopedic deconstruction of the 34 specific architectural techniques required to scale a fragile prototype into a resilient agentic system. We begin with Technique 1, Agentic RAG. Instead of forcing every query through a static vector search, an orchestrator LLM acts as an intelligent switch. It evaluates the user's intent and dynamically routes the request to either a semantic chunk search or a full document retrieval tool. Compare this to Technique 2, Basic RAG. The industry standard baseline simply converts incoming text to embeddings, calculates cosine similarity, and retrieves the closest vectors. It is fast, but entirely inflexible. Technique 3, RAG with CSV files, adapts this baseline for structured data. You serialize tabular row data into readable text strings, wrapping each block with precise integer metadata, allowing the system to accurately retrieve specific rows from a database export. Technique 4 introduces Reliable RAG. This installs a dual LLM judge setup into the pipeline. If context is off topic, a relevance gate forces a query rewrite. A grounded gate ensures output matches the evidence. This reduces hallucinations to 0, but with a severe latency trade-off. Multiple evaluator prompts drive compute costs up exponentially, restricting this to high-stakes domains. To improve accuracy without the compute penalty of an LLM judge, we use Technique 5, optimizing chunk sizes. This is an offline brute force method. You index your data at multiple chunk ratios, say 256, 512, and 1000 tokens, and run regression tests to find the exact mathematical overlap that maximizes recall for your specific dataset. Shifting to dynamic validation solves hallucinations, but the compute overhead forces engineers to intercept and optimize queries before they ever reach the database. This brings us to pre-retrieval, starting with Technique 6, proposition chunking. An LLM reads your raw paragraphs and fractures them into atomic independent factual statements. By indexing these isolated facts, you eliminate the narrative noise that confuses vector matching. Technique 7 handles query transformations. Users rarely ask perfectly structured questions. Here, an LLM intercepts a vague prompt and splits it into multiple precise, faithful subqueries, running them in parallel to maximize surface area coverage. Technique 8 is hide, or hypothetical document embedding. When a query is too sparse to match a complex document, the system generates a hallucinated, ideal answer. This synthetic text is embedded and acts as a semantic magnet to pull in real documents. Technique 9, hypothetical prompt embedding, flips this logic. It generates task-specific instructions, pulling retrieval towards structured analytical documents. Technique 10, contextual chunk headers, operates during ingestion. You systematically prepend the parent document title and specific section path to every single text chunk. This guarantees that an isolated sentence retains its structural origin. A vector database can only match exact coordinate distances. Transforming the text and the query aligns the mathematical search space with the user's intent. After retrieval, we must sculpt the data to fit the LLM's strict token limits. Technique 11 is relevant segment extraction. An LLM scans the retrieved documents and surgically extracts only the sentences addressing the query. Conversely, Technique 12 solves the opposite problem. When a chunk lacks context, the database automatically fetches preceding and following chunks, snapping them into place to restore flow. Technique 13 is semantic chunking. Instead of slicing text every 500 characters, the system calculates cosine similarity between adjacent sentences. It only places a chunk boundary when the mathematical similarity drops, indicating a natural topic shift. Technique 14 is contextual compression. A secondary, smaller language model intercepts the retrieved chunks and rewrites them into a dense summary, strictly filtering the text to save generation tokens. Technique 15, document augmentation, happens entirely at index time. An LLM predicts 5 questions a text could answer and permanently glues them to the chunk to boost search recall. LLM context windows are computationally expensive and prone to distraction. These post-retrieval interventions act as scalpels, ensuring the final generation model only processes high-signal evidence. Relying on a single vector index creates blind spots. Technique 16, Fusion Retrieval, runs dense semantic searches in parallel with sparse BM25 keyword searches. The reciprocal rank fusion algorithm merges the results. Next, Technique 17 introduces re-ranking. A fast retriever pulls 20 candidates, which are ruthlessly rescored by a heavy cross-encoder model to identify the true top 5 results. Technique 18 applies multifaceted filtering. Before the similarity search even executes, strict SQL-style metadata parameters like tenant IDs and user roles are injected, physically masking out unauthorized data. Technique 19 uses hierarchical indices. For massive corpora, the system executes a coarse search against a database of document summaries, isolates the winning document, and then drills down into a secondary index of specific text chunks. Techniques 20 and 21 are ensemble and dartboard retrieval. You query multiple specialized engine types simultaneously and apply maximum marginal relevance algorithms to forcefully penalize redundant information, ensuring topical diversity. First-stage retrieval is merely a wide net. The true intelligence of a modern architecture lies in the deterministic secondary ranking algorithms that filter that net. Moving to Technique 22, Multi-modal RAG. During ingestion, vision models generate rich, descriptive text captions for diagrams and screenshots. These images can now be retrieved dynamically using standard text vector searches. Techniques 23 and 24 focus on telemetry. Retrieval with feedback loops continuously updates re-ranker weights based on user clicks. Meanwhile, adaptive retrieval uses an intent classifier to route legal queries to a policy database and technical queries to a specialized hybrid search. Technique 25 is iterative retrieval. When facing a complex research request, an LLM enters a multi-hop loop. It reviews a first pass of retrieved data, identifies what evidence is still missing, and autonomously generates follow-up queries until the context is complete. Technique 26 is deep eval. Production RAG requires automated CI/CD testing harnesses. Every architectural tweak is evaluated against a golden dataset, scoring outputs for correctness, faithfulness, and relevancy, preventing a deployment regression. Techniques 27 and 28 cover grouse and explainable retrieval. These methods enforce extreme groundedness checks, allowing the system to output auditable, inline citations mapped directly back to the database chunk index. Building enterprise RAG is a software engineering discipline. It demands rigorous regression testing and auditable telemetry, not casual prompt engineering. The cutting edge relies on knowledge graphs. Technique 29, GraphRAG with LangChain, extracts entities from the query and traverses a Neo4j graph to map relationships, using node IDs to filter the vector search. Technique 30, Microsoft GraphRAG, solves corpus-wide questions by pre-computing hierarchical community summaries across the graph, providing an instant macro view of the dataset. Technique 31, Raptor, executes a similar macro view using a recursive summary tree structure, allowing the retriever to seamlessly drill down from high-level abstractions to highly specific text sleeves. Techniques 32 and 33, Self-RAG and Corrective RAG, grant the LLM the authority to decide if a database retrieval is even necessary, and triggers live web search fallbacks if internal search scores fall below a strict threshold. This leads to our final evolution, Technique 34, the Sophisticated Controllable Agent. It replaces chaotic, free-form language models with a strictly deterministic decision graph. It forces explicit planning, strictly verified queries, and auditable memory states at every step. The endgame of enterprise RAG is, ironically, about removing LLM autonomy. You achieve scale by trapping the generative power inside rigid, auditable control structures. This chart displays the integration reality. No production system implements all 34 techniques simultaneously. Building a RAG stack is a continuous exercise in deciding which architectural trade-offs to accept across cost, complexity, and latency. The standard prescription is to build the foundation first. Lock in basic RAG, optimize your chunk sizes, and implement Fusion Retrieval with BM25. Do this before introducing the compute overhead of agentic loops. If your use case demands extreme accuracy and latency is not a constraint, layer in iterative retrieval loops and two-stage cross-encoder re-ranking to guarantee precision. True system architecture isn't about collecting features from a list. It is about understanding the underlying code-level logic of these models to systematically solve the exact bottlenecks hiding in your enterprise data.